Welcome to Quantum Photonics. So we have a very interesting topic today. It's about energetic particles. Energetic particles, also known as cosmic rays, are a fundamental component of the universe, playing a crucial role in astrophysical processes and influencing the evolution of galaxies. These particles, which include protons, electrons, and atomic nuclei, travel through space at nearly the speed of light, carrying with them clues about the most violent and energetic events in the cosmos. Uh, Energetic particles in the universe delves into the origins, propagation, impact of these high energy particles, and it provides insights into the sources of cosmic rays such as supernova remnants, active galactic nuclei, gamma ray bursts, and um, also provides us with mechanisms by which these particles are accelerated to relativistic speeds. So we have here our special guest speaker, uh, Dr. Siyao Xu, Professor Siyao Xu, who is an assistant professor at the University of Florida. She had her PhD at the Peking University, and later on, she was a Hubble Fellow at the University of Wisconsin-Madison and was a Hubble Fellow also in the Institute for Advanced Study in Princeton University. She had the International Union of Pure and Applied Physics Award, the Young Scientist Prize in um, Astroparticle Physics in 2019, and the Cecilia Payne Gaposchkin Doctoral Dissertation Award in Astrophysics in 2019 as well, and the International Astronomical Union PhD Prize in 2017. Her research group delves into the study of theoretical astrophysics, and her research interests are in MHD turbulence, magnetic recognition and turbulent dynamo, cosmic rays, star formation and interstellar medium, and high energy astrophysics. So later on, I will try to link her profile here on the room chat. Her selected publications will be attached here on the profile. And just to tell you about some of the titles, the publications are about wide binary stars formed in the turbulent interstellar medium, um, the turbulent reconnection acceleration, quasi-perpendicular shock acceleration and tidal disruption event radio flares, and on the injection scale of the turbulence in the partially ionized local interstellar medium, and statistical measurements of dispersion of measure fluctuations of FRBs. So these are some of the publications that our guest speaker had published. So yeah, we are very excited to see and try to sing, hearing from her about the slides that she had given us, posted at the top of the screen. So yeah, we are eagerly welcoming our guest speaker, Professor Siyao Xu. Welcome to Quantum Photonics, Siyao.
Yeah, thank you so much, Cecile, and thank you so much for the wonderful opportunity for me to chat with you, everyone, here about my research on cosmic rays. Shall I start? Okay, so
Yes.
yeah, so let's start with the second slide, slide number 2. So this slide, you can see that this is um, experiment done back to 1912. So about 1 century ago, people already realized there are some mysterious radiation um, in the atmosphere. Well, the idea at that time was the radiation came from the rocks on Earth. So we would expect that if this is the case, then if we go to higher in the atmosphere, the radiation level and rate should decrease. So this experiment was done by Victor Hess in 1912. This is a balloon experiment that took him about 5,000 meters from the Earth. And surprisingly, he found, in fact, the radiation rates is much higher compared to that at the ground, this at the sea level. And also, he found that during the experiment, there was solar eclipse, but there was no drop of the radiation. So he concluded that this radiation does not come from the Earth, not from the sun, it comes from the outer space, the deep universe. And this radiation is so strong that it can penetrate the atmosphere and cause the ionization of the atoms, molecules in our atmosphere. And in fact, this is cosmic ray. So cosmic rays are energetic charged particles originate from the universe, the outer space. And in fact, uh, as you see that this is a very old, century-old subject. But recently, it also attracts a lot of attention from researchers in astrophysics, in cosmology, as this is one of the four messengers from the universe. So the other three messengers we know are photons, gravitational waves, and cosmic neutrinos. And in fact, the cosmic rays, these energetic particles, they are closely related to other messengers, high energy photons and high energy neutrinos. These are mostly protons, and there are also other small fraction of other heavier elements, electrons, positrons, and they have very high energies with a speed close to the light speed. So before we talk about how these particles get accelerated, gain so high energy in the universe, let's move on to slide 3. So on Earth, we also can produce very energetic particles with speed close to the light speed by particle accelerator. So if we think about the basic physics, how an accelerator works, how to design a particle accelerator. So to accelerate a particle is similar to accelerate any object. You want to give it a kick. So you want to apply a force to accelerate it. Um, so in accelerator, this kick, this force can come from electric field. So if you go to next slide, number 4, on the left, this is the section in accelerator. There is an electric field. So the particle beam in the electric field feel the electric force and get accelerated. So if we have a really, really long accelerator and the particle move along a straight path, in the electric field can get accelerated until achieving a high energy. But you see, there is a problem in this linear type accelerator that you really need accelerator to be super, super long for the acceleration to be strong, for the particle to really reach very high speed. So there's a smarter way to do this. So on the right, this illustration for the important role of magnetic field in accelerator. So the magnetic field, we know its force, the Lorentz force, is in the direction perpendicular to the particle velocity, the moving direction. So it does not directly contribute to changing the speed of the particle, but magnetic field can change the direction of the particle's moving direction. So it can, instead of moving along a straight path, the magnetic field can bend the particle, can move them in circles. So if the particles move in circles, it means that they can repeatedly get accelerated again and again by the same acceleration section with the electric field on the left. So you see the combination of electric field and magnetic field, they work together, can give the particle repeated acceleration in the accelerator with a limited size. So that is happens in real accelerator. For example, uh, next slide 5. This is an example of uh, the accelerator. You can see that the particle is showing the particle moves in circles because of the force of magnetic field, and with the repeated acceleration, it can eventually reach a very high energy. For example, in the LHC, the Large Hadron Collider accelerator, the fastest proton achieved can have energy about 70 eV, so you can see that it's very close to the speed of light. Well, this is a quite successful accelerator, but if you compare the fastest particle we produce on Earth and the fastest cosmic ray particle the universe produces, we see the big difference. Just count how many 9 for the cosmic ray particle. So in terms of energy, so here I put the number GeV is equal to 10 to 9 eV. So TeV is equal to 10 to 3 GeV. So you can see there's still many orders of magnitude difference. So the universe can produce much higher energy for the cosmic rays. Well, the reason is to increase the energy of the particle, we really need a strong magnetic field that can effectively bend the particle's moving direction. And we also need to build really large accelerator. So the larger size of the accelerator is, the stronger the magnetic field strength is, the higher energy we can achieve. So you can imagine, so we have the experience of driving on a curvy road on a mountain. So if the turn is very tight and the magnetic field is not strong enough, it's very easy for the particle to fly off course. So the solution to this is to build large accelerator and have a smaller curvature of the particle trajectory with a given magnetic field with current technology. The universe, of course, can have much larger accelerator. The size of accelerator on Earth, of course, is limited by cost and is definitely limited by the size of the Earth. But in the universe, there can be different types of accelerators, and that can be much larger. For example, on the next slide, number 6. So here I show on the left is example of a cosmic accelerator. This is the X-ray image showing the expansion from a supernova. So this is explosion that happens when a massive star at the end of its life. So the star explodes, and that drives very strong shock wave expanding toward the surrounding medium of the star. We call it interstellar medium. And for shock wave, so we know, for example, so we know why. Imagine that we are now sitting in the same room. So when I talk, I create this vibration in the air, the variation of the pressure change in the air. But I do not need to be very close to you for you to hear me, because this vibration in the air can travel through the room to reach you and carried by sound waves. So you receive the information, you know there's a change of the vibration in the air pressure by receiving a sound wave. So the difference here is the shock is a disturbance, but this disturbance propagates very fast. It is faster than the sound speed in the medium. So it means that there's no way for you to know there's a change of the air pressure until the disturbance, the shock, already arrives, already reaches you. So you can imagine that. So this creates a sudden change in density, in air pressure, in temperature. So it creates a discontinuity of these physical quantities in space. because it's really happens so fast that you don't know anything before it arrives. So on the right, I use this vertical solid line to represent this shock front or the discontinuity. You can see that on uh, either side of the shock, on both sides of the shock, I use different color to represent the sudden change of the physical quantities uh, in front of the shock and behind the shock. So we usually call the medium in front of the shock, the light gray color here is the upstream, and the dark side behind the shock is called the downstream. And shock is a compression, it is a converging flow. So it means that on either side of shock, no matter you are sitting in the upstream in front of shock or in the downstream behind the shock, in your reference frame, you see the flow approaching you with the same speed. So you always see the flow from the opposite side of the shock coming to you with a speed as a fraction of the shock moving speed, this u here. And again, note that u is a fast speed. It is larger than the sound speed, the information propagation speed in the medium. Okay, so in terms of acceleration, you can imagine that. So now we are at slide number 7. Okay, so on either side of the shock, because you see the flow coming to you with a faster speed, from the other side of the shock, imagining this is a fast moving train, and every time you cross the shock from one side to the other side, it means you get on board of the fast moving train, and you can get energy of the kinetic energy of the fast moving train every time you cross the shock. So it means that so this is a one acceleration. If you can manage to cross the shock many times, it means that you move from the upstream to downstream and from downstream back to upstream, again, back and forth, you will repeatedly get accelerated. So this is the mechanism known as shock acceleration. It is the mechanism to accelerate particles to become cosmic rays by the cosmic accelerator. Um, so another analogy people usually like to use is ping pong ball. So if you go to next slide 8, so here you can see the illustration. Now it's not the person getting accelerated, it's this ping pong ball, the particle gets accelerated. So imagine this particle we are talking about is this ping pong ball. Every time it crosses the shock, it gets accelerated because it gets kicked by the flow coming to the ball from the other side of the shock. And if the ball can cross the shock back and forth many times, it can get continuously accelerated by multiple kicks from the by the flows coming from the opposite side of the shock. So this was known by Fermi as is known as the Fermi's first order acceleration to explain this shock acceleration of cosmic rays. So you see the energy source here, of course, is the kinetic energy of the shock wave coming from the explosion of the star. But the key element here is how the particle can stay long near the shock. Imagine if the particle escapes, drifts away on either side of shock, it wouldn't go through these multiple cycles of shock acceleration. It wouldn't reach a very high energy. So here it's very similar to what we do on Earth. The nature also creates very strong magnetic field on both sides of the shock. So the importance of magnetic field here is also similar to our accelerator on Earth to confine the particles. It makes sure that the particles stay near the shock for sufficiently long time on either side of the shock, both sides of the shock, for the particle to get accelerated again and again. Eventually, the particle reaches so high energy, is so high that the magnetic field are unable to confine it anymore, and that is gives the maximum energy of the particles accelerated by this shock accelerator. So I'm going to talk about next one mechanism, how the magnetic field can confine the particles. So now we are at number 10. So here you can see on the left, these are the magnetic field lines. So we need a particular magnetic field configuration to confine particles. So usually in the textbook, we learn about uniform magnetic field. So then the field lines are straight lines going in one direction. But here we see the magnetic field lines are converging to the mirror point. So the converging point, we call it mirror point. I'll explain why it is called mirror later. So you can see the field lines, when it gets together, compressed together, the magnetic field strength increases toward the mirror point. There is a very important physical quantity we'll use to explain this mechanism, which is on the right. This is a ratio, which is called adiabatic invariant. So in nature, we have different types of adiabatic invariant. It describes some quantity that can approximately keep constant when some process happens slowly. So in this process, we have something changes, which is the magnetic field. So as I described on the left, so the magnetic field strength changes. It becomes stronger toward the mirror point. And this process happens slow enough for the quantity, this ratio, the first adiabatic invariant, to be constant. So here M is the particle's mass, and V perp is the particle velocity perpendicular to the magnetic field direction, and B is magnetic field strength that changes. So this constant ratio comes from the constant angular momentum. So we know the conservation of angular momentum. If we imagine, so a charged particle in magnetic field, their motion around magnetic field is gyration. So during this gyration, they have their angular momentum constant, conserved. And from that, you can get this ratio here is a constant. So what it means, so when the particle moves from the weak field region to a stronger field region, it starts to feel the change of the magnetic field strength. And accordingly, to keep its angular momentum conserved, its velocity perpendicular to magnetic field also increases. So then, so if the particle has its total velocity conserved constant, it means the parallel component of its velocity must decrease. So it means when the particle, if you see this right arrow showing the direction of the particles moving toward the magnetic mirror point, its perpendicular velocity increases and its parallel velocity decreases. It means the particle moves slower and slower approaching the mirror point. And when it gets to the mirror point, its parallel velocity can decrease to zero. It stops. And the next moment, the mirror force, the magnetic force, would drag it back and push it back to the weak field region as indicated by the blue arrow. So you see the particle gets reflected. It reverses its moving direction at a strong magnetic field mirror point. So this is how its names come from. Similar to mirror, we know that mirror can reflect light. Here we are discussing the magnetic mirror. The magnetic mirror can reflect charged particle because of this particular configuration of magnetic field. So this is a well-known mechanism. In fact, it has been applied to fusion experiments to confine particles. So here, it is also a mechanism that can happen in the universe to confine particles near the accelerator. So here, we can do experiment. If you go to next slide, number 11. So here is example how we study this in computers. So for many astrophysical problems, because we are dealing with really, really huge scale astrophysical systems, it's not easy to perform experiment in lab. So what we usually do is we run some simulations. So it's like experiment in computers. So here on the left, these yellow lines show the magnetic field. So we say in reality, magnetic fields are not straight lines. They have perturbations, and these perturbations are usually caused by the turbulent motions in the medium. So we know turbulence very well. It exists everywhere. For example, you definitely feel turbulence sometimes on the plane, and you also see turbulence in your coffee when you stir the coffee, so you can see the turbulent motions in fluid, in air, everywhere in our daily life. And in the universe, turbulence is also everywhere. For example, we say these explosions of stars. This also drives turbulence in the surrounding interstellar medium. So these turbulent motions can cause the perturbations of magnetic field. They can change the magnetic field directions. They can also compress the magnetic field, create these magnetic mirrors that I showed in slide number 10. So when it compress the magnetic field, it naturally creates this magnetic mirror structure that exists everywhere in our astrophysical medium. By the way, so we know that Voyager, the spacecraft Voyager, got out the heliosphere. So heliosphere is the medium regulated by our sun, our local medium. So the interstellar medium is the medium outside the heliosphere, so where the medium other stars contribute and affect in our galaxy. So Voyager now is already in the outside the heliosphere in the interstellar medium, and there it for the first time detects the magnetic fluctuations in our galaxy, and it does see a lot of magnetic fluctuations and change in magnetic field strength. So in a picture similar to what I illustrate here on the left in our simulations. So you can put energetic particles, these cosmic rays, in such turbulent magnetic fields, and to test that idea that I showed earlier in number 10, the magnetic mirroring effect on cosmic rays. So on the right, this is done by my student Charles Zhang. Is example of the particle trajectory. So we charge the particle there, and we can trace the particle how it moves in space. So this is charge the particle, and there is a magnetic field, and because the magnetic field has this magnetic mirroring structure, you see the particle does not move along a straight path. So you see its trajectory has this very interesting pattern. It goes back and forth. It repeatedly reverses its moving direction. So how do we know that a particle uh, undergoes this mirror reflection? So we can measure this magnetic moment, this adiabatic invariance, this constant ratio that I show in number 10. And we indeed see this ratio during this process is a constant. And here the particle trajectory is color-coded by magnetic field strength. So you can see the color changes means the magnetic field strength changes. So the particle every time it moves from a blue color region, the weak field region, to a stronger field region, the red color region, moving to the mirror point, it gets reflected. It gets reflected again and again because it doesn't move along a straight path. It continuously reverses moving direction. So you can see this is a very effective mechanism to confine the particle in space. Imagining after there's a shock, because the particle can repeatedly reverse its moving direction, which means that it can always go back to the shock, cross the shock from upstream to downstream and downstream to upstream. So it can get repeated accelerated by this good confinement by magnetic field. Okay, so So I have talked about shock acceleration and this mirror mechanism to confine the particles in the shock accelerator. But in the universe, there are different types of accelerators and there are different accelerating mechanisms. So for the shock accelerator, the energy comes from the kinetic energy of the expanding shock wave of the star. There are some also other accelerators with the energy coming from the very strong magnetic energy. Because the acceleration physics is so complicated in nature, for example, we need to understand how magnetic field is amplified, how the magnetic field becomes so strong, and what is the magnetic field configuration there is, and how it can confine the particles. So because it's so complicated, um, we have to say that after the discovery of cosmic rays, already a century, it's still an opening question. What is the origin of high energy cosmic rays? So now we are moving to the last slide, 12. So the question, where do they come from? Especially for the very high energy cosmic rays in the universe. So it's not clear what is exact acceleration mechanism and where the accelerators are to generate these cosmic rays that we see on Earth. So I said one reason is because acceleration physics is so complicated, so we don't clearly understand everything. Another reason is that, so here is illustration for the cosmic ray trajectory in the medium in the galaxies and medium between galaxies from their source to Earth, our Earth observer. So the turbulence and magnetic fields that I mentioned, they are everywhere in the universe. So the magnetic fields in all astrophysical medium are turbulent with magnetic fluctuations. So when a particle gets accelerated from its source, from the accelerator, it doesn't move directly to the Earth along a straight path, but it moves diffusively by their interaction with the turbulent magnetic field. So we can see that because their trajectory changes so much in the astrophysical medium, when they arrive at the Earth, we can detect the direction of their arrival, but unfortunately, this direction is already very different from their original direction when they leave their source. So by detecting the direction where they um, arrive at Earth doesn't tell us anything about where the source is. So because the particle already loses memory by this diffusion process. In fact, it's interesting that because when on Earth we see all particles, cosmic rays, in fact, they arrive at us isotropically, so as if they come from all possible directions. So, in fact, the last century, some people believe that cosmic rays are produced everywhere in the universe, but this is not true. We now know that there are particular sources that are able to accelerate these particles. In fact, this idea was already proposed by Vitaly Ginzburg, a Nobel Prize winner, who proposed that uh, cosmic ray diffusively move in space, and that cause their isotropic arrival direction at Earth. It's not because they are generated everywhere in space. So yeah, so this is an open question still, and we are still on our way to study the origin of cosmic rays. And as I said at the beginning, because cosmic rays are so closely related to photons and neutrinos, so understanding the source of these energetic particles can also help us understand other messengers from the universe. Okay, so I will stop here, and thank you very much for listening.
Thank you so much, Siyao. So, yeah, we'd like to inform the audience that we are opening the floor for questions. So please raise your hand if you have some questions. We will give you an opportunity to ask our guest speaker. Just to reset the room, I would like to reintroduce our guest speaker, um, Professor Siyao Xu, who is now an associate professor at the University of Florida. And of course, I'd like to mention that I am thanking Alexander, Dr. Alexander Lasarlian, because he tried to introduce this speaker. Her former mentor tried to recommend
Mhm.
Dr. to talk to us on this forum. And indeed, it was a very interesting talk with amazing slides. Dr. Su had her PhD from Peking University. She was a NASA Hubble Fellow at the University of Wisconsin-Madison, and she was also a NASA Hubble Fellow at the Institute of Advanced Study in Princeton from 2020 to 2023. She was awarded this International Union of Pure and Applied Physics Award, the Young Scientist Prize in Astroparticle Physics in 2019, the Cecilia Payne Gapos Ching Doctoral Dissertation Award in Astrophysics, and the International Astronomical Union Award PhD Prize in 2017. Her research group is involved in theoretical astrophysics, and her interests are in MHD turbulence, magnetic reconnection and turbulent dynamo, cosmic rays, star formation, and interstellar medium, and high energy astrophysics. So, yeah, that is our guest speaker. Xiao, I will pass on the microphone in a while to our other speakers here in the room. I would like to just ask a general question for our general audience. Um, we have spoken about cosmic rays, and um, how significant is this study that you're having about cosmic rays to the um, to our applied understanding, and can you elaborate it on um, can you elaborate on the primary sources of cosmic rays and explain the mechanisms by which the sources accelerate particles to high energies? Yeah, that is my question for the audience. Ah, I don't know if your mic is open, CL.
Oh, okay. Yeah, so this is a both old and also new subject. Old because its discovery happened about 100 years ago already, and many great minds in history have already contributed significantly to this field. And it's new because there are many new observations after 2000. There are like both ground-based and space-based telescopes, and have a lot of new, more accurate uh, measurements on the cosmic rays with a larger energy coverage and also high sensitivity. So these particles, they have more than 10 orders of magnitude in energy coverage, and they have uh, and they have many interesting phenomena uh, related in astrophysical studies, and the explosive interest on this subject in recent years is also related to the detection of high energy neutrinos by S-Cube. And the generation of high-energy neutrinos is comes from the interaction of these cosmic ray particles with the matter around them, the interstellar matter around them. So understanding how these energetic particles are accelerated in the universe give us a lot of insight, new insight to explain other mysterious observations and detection of other messengers. So now the multi-messenger astronomy is really the frontier of astrophysical studies. So and with a lot of new telescopes and surveys to try to detect more multiple messengers coming from the same source. So because of their physical connection, so when the source is identified as efficient accelerator of cosmic rays, it's also very likely there will be other messengers, photons, and high energy neutrinos detected from that source. So from my research perspective, we focus on the fundamental physics, on the acceleration mechanism of these particles, and how the magnetic fields there play the important role for the acceleration to be efficient. So you see, the nature has a lot of energy stored in different astrophysical objects in different forms. Sometimes the energy is in the kinetic energy, sometimes the energy is in magnetic energy. So there's a lot of source of energies, but the key question is how this energy can efficiently converted to particles. So you need energy to be converted from one form to another form efficiently. Um, so to produce these very, very high energy particles, and then how these particles interact further with the magnetic field along its very, very long journey. So these cosmic rays can come from some accelerators, these supernova explosions in our galaxy, but very, very high energy cosmic rays are believed to come from other galaxies. So they have extragalactic sources. So they really need to travel their own galaxy and the medium from their galaxy to our galaxy, and our galaxy eventually reach our Earth. So every high energy particle coming to Earth, they experience a lot of physical processes, and we need to understand basically every piece of the physics during their journey, during their acceleration, to eventually understand the observation we obtain on Earth. So yeah, I would say this is a lot of exciting progresses happening in this field, and uh, although it remains very, very challenging for us to answer the origin of these particles, but I think we are getting there with both recent development in observational techniques and also in our theoretical understanding of the complex physics. Yeah.
Yeah, thank you so much, Siyao. So, yeah, if there's time, I will ask more questions later. But in the meantime, I'd like to acknowledge Frank, of course, who is one of our moderators, and also Nas, who are on stage. So, I'd like to give the mic to Frank.
Yeah, thanks, Cecile. Yeah, thanks, Cecile, for the wonderful lecture you shared. Yeah, the again, as Cecile mentioned, that we uh, appreciated the team is earlier. The great lecture Alex, Dr. Lazarian has gave us. I guess I remember more than one lectures. The one I remember have some deep, very strong impression on me is the gigantic magnetic field in the cosmos, and I'm still puzzled by where they come from. It's so huge, and so there's such a interesting pattern, intergalactic. Well, he explains some mechanism how these pattern shape itself, and also a way of picturing. I think this has to do with a synchrotron kind of polarization. Is very interesting. The for this for your what you the problem that you mentioned, it's amazing that it's still an open question. And the regarding the, I remember you mentioned the on the slides with the, sorry, the slides number. Oh, there's a slides that explaining the shockwave acceleration uh, mechanism. The I was wondering, the in order for the particle to be repeatedly coming back and forth, the front and the back end of the shock wave. So there has to be some kind of you mentioned magnetic mirror effects. Does that mean the magnetic field is along the shock wave, or I'm a little bit I guess
Uh-huh.
confused here.
Yeah, thank you so much, Frank. Yeah. So, right. So, okay. So since you start mentioning this magnetic field that I was not there, but I guess Alex was talking about. So they have this new technique of detecting magnetic field in the universe, and it's so important for us to so I mentioned that Voyager has the direct measurement of the magnetic field, but magnetic field is invisible. So we have the question like, how can we detect something invisible in the universe? Although we know it must be there, but it's also so difficult to measure them. And by the way, so I mentioned this diffusion idea of cosmic rays from last century was first proposed by Ginsburg. Uh, and in fact, Ginsburg was also the mentor of Alex. So and Alex did a lot of important pioneering work on cosmic rays, and I have been working with him on this new mechanism of mirror diffusion that I show on slide 11. So for this mirror, okay, so the traditional idea for the shock acceleration, so the shock acceleration by itself is called first order Fermi acceleration. In fact, back to 1949, Fermi's original idea, now today we call it second order Fermi acceleration, in fact, is the mechanism that people traditionally use to understand how the particles are confined in turbulent magnetic field, for example, near the shock. So that idea is that imagining when we drive the car on a very bumpy road, so the car gets in interaction with the bumps on the road. So these are magnetic fluctuations. So every time when the particle feels magnetic fluctuations, it can get scattered. So it means the particle can have a small change of its moving direction. So like any diffusion process, after many times of the random change of its moving direction, eventually this accumulation effect will cause a significant change of its moving direction, which means the particle loses its original initial memory of its initial moving direction. So we usually call this corresponding length as its mean free path or the step size of its random walk. So Fermi's original idea is there's a lot of these magnetic bumps. In his language, he called them magnetic clouds. So these a lot of magnetic small clouds on both sides of the shock. So then particle by get scattered by these magnetic clouds, and they randomly change their moving direction for them to be confined in the flow, either upstream or downstream. So you need a lot of magnetic fluctuations on both sides of the shock. So that is the Fermi's idea. So here what I talk about is the magnetic mirroring effect. So as I showed that this also comes from the magnetic fluctuations. In particular here we stress the change of the magnetic field strength. So it's not just the magnetic field orientations as I show here in number 9. This is basically illustrates, this is from textbook picture of long hair's textbook. It shows the change of the magnetic field directions. But in this mirror picture, what I want to stress is the change of the magnetic field strength. And that caused not a random change of the particle, but the reversing of the particle moving direction. So so if there are a lot of magnetic mirrors on both sides of the shock, or depending on the size of the mirror, if the mirror size can cross the shock, then the particle can go back and forth. So yeah, as you said, it depends on the orientation of the magnetic field. If the shock is moving in the direction parallel to the magnetic field, then it will be very efficient reversing of the particle crossing the shock many times. But even you have some randomly orientated magnetic mirrors with smaller size on both sides of the shock, they can also play the role similar to the scattering for the particle to randomly and change their moving directions. So this would make the particle, you see, we are talking about light speed particle. If they move along a straight path with a light speed, they will very quickly escape from the shock. But because they repeatedly change their moving direction, this diffusive motion of the particle makes them effectively coupled to the fluid. So if you look at the particle, the global motion of the particle, they do not really move much. Although if you trace the individual particle, they still move with light speed, but because they move diffusively, the particle doesn't seem to move much on both sides of the shock. So that is the idea how the particle can repeatedly feel the difference between the flow speed on both sides of the shock and gets accelerated. Yeah,
Oh,
I
I
hope I
see. Yeah,
explained it well.
yeah. Thanks. That clarifies things a lot. Thank you. The so then I have a interesting following up. I mean, so I mean it's a very interesting question that you posed. The is it possible, since we're talking about charged particle that are very high speed, so uh, given the very short distance in we observe on penetrating the atmosphere, there is not enough length to detect any curvature in the path penetrating the Earth. Is it possible? Because if it is possible, then there's can be a little bit of information on the source, the location.
I see. Yeah. So you are right that so for example, there are some relatively close sources. For example, some pulsars that produce uh, uh, electrons, positrons, and we also consider them as cosmic ray particles. And the if the distance from the source and Earth is shorter than the mean free path of the particle, which means they haven't completely lose the memory of their initial condition, the moving direction, then we can know approximately where these particles come from. Um, well, it also depends how turbulent the magnetic field is, and because we have poor knowledge of the magnetic field, and so there are some new techniques that Alex Group developed to map the magnetic fields in our galaxy. Uh, but if the magnetic field is very rough, very turbulent, it also means the particle can easily lose its memory. And also, the mean free path depends on the particle energy. So if we have very, very high energy cosmic rays, then it's more difficult for them to lose memory. But unfortunately, our galaxy is not very active galaxy anymore. So it doesn't have, it's believed that it doesn't have the ability to really accelerate the cosmic rays to the high energy end that we observe. So because of these very high energy cosmic rays, they come from other galaxies. So yeah, so even they have large mean free paths, but when they reach the Earth, the distance is too large. So we still don't know clearly where the sources, the directional sources are. So we don't have a good mapping of and identify which particular source account for the accelerator of these high energy cosmic rays.
Yeah, I got it. I think I made a mistake in stating, earlier the quote unquote source. By source, you mean the charged particle, which supernova, for example,
Yeah.
first generate. Okay, that's the source. I was referring to the last, I guess, magnetic mirror that flame shots the ray to Earth, because from your picture, the mirror picture that you shared, seems that the the parallel velocity become almost zero, and then the cyclotron, I mean the circular velocity become huge, right? So that's supposedly that's the one that we observe we found on Earth. So that's why I was I was referring to maybe we can have the last and maybe can match the turbulent pattern or mean free path. Although it's random, but there's supposed to be a fixed congregation of the. I don't know if that's data is available already or the magnetic field pattern, how turbulent it is. But yeah, that was my point. But by the way, the solar rays, I mean those particles are very relatively low energy, right? Just to confirm.
Yeah. So yeah, right. So I should better explain that. Yeah, number 10. This is showing. In fact, it's a macroscopic picture. So it's so we are dealing with a really huge range of scales. For example, when we talk about GeV cosmic rays, and they have the size of the gyration is about a few solar radii, so the size of the sun. But when we go to even, let's say, PeV cosmic rays, that is believed the highest energy that our galaxy can produce, but their gyro radius is already a few parsecs. So it's already the size of the explosion size of the massive star. So that is much bigger than the size of the sun. So, and if you go to higher energy, then their gyro radius can be larger even than the entire Milky Way. So, because we are dealing with this many orders of magnitude in length scales, so this mirror here, it can be all different sizes. So it produced by turbulence on all different scales. So here is more like a macroscopic process to explain the diffusion on each step of its random walk. And eventually on global scales, it gives this diffusive trajectory of the particles, but this just the mirror I showed is probably just a small piece of its the particle entire trajectory. Yeah, and yeah, so in fact, Voyager, one factor we believe Voyager enters the interstellar medium because they start to see the drop of these low energy particles from the sun, but start to see the increase of the high energy cosmic rays in the outer space in the interstellar medium, and that is important for people to decide. Oh, Voyager enters the interstellar medium, yeah, around 2012. Yeah.
Yeah, thank you. Yeah, this thanks for all the answers. Yeah, very interesting.
Thank you.
Thank you, Frank. Thank you, Siyao. So I would like to acknowledge Kevin and also Dash, who recently came on stage. So, but for now, I'd like to give the mic to Nas, who has been waiting patiently. Nas, would you like to speak now?
Sure, thank you. Thank you, Sia, for your Cecile and Sia excellent presentation.
Thank you.
I have one question in three parts. We don't know the origin, or not yet, but do we know the cause of these cosmic rays? And the second part, are there any evidence of health damage to the earth or the plants or any biohazards? Because after all, cosmic rays, whatever it is, can interfere with life on Earth. Are there any evidence to that, or has been any studies to avoid the damage that these may cause to life on Earth?
Okay, yeah, very nice question. So I said we don't know the exact source of for particular observed cosmic ray. We do have some understanding on the candidates. So there are several promising candidates accounting for the origin of the very high energy cosmic rays. So apart from these shocks of a supernova explosion, there are also the powerful jets from accretion disk from black holes. And also some like very explosive, we call them gamma ray burst. So it's also the high energy ejector, uh, and there can be very strong magnetic field and also very large kinetic energy. So we know there are sources definitely with there are huge reservoirs of energies. So the not so clear part is the details. So the detailed physics, for example, the efficiency for the energy from magnetic field or kinetic energy to particles, and whether some mechanism can universally explain all observations from different messengers. So there are some details which is not agreed by the community, but there are some candidates. We probably are still waiting for both sides, both the more studies from both the theoretical side, and also we are waiting for more observational evidence that more conclusively tell us a particular source with very solid, strong evidence to tell this is the origin of cosmic rays, the high energy cosmic rays. Yeah, I think this may happen soon. For the hazard on Earth, so yeah, this is radiation. So even the last century, people start to realize these radiation already can spoil their experiments. And for our humans, basically, we are all under the shower of this cosmic radiation. Basically, you feel energetic particle through your body, one particle per second, something like that. So, and there also research saying people who fly a lot may get more radiation compared to people who do not travel much. And it's also a very interesting question for studying on exoplanets. So our sun has its own magnetic field. So the heliosphere region is the region controlled, regulated by the magnetic field from the sun. So that magnetic field can help us protect us from the cosmic rays. So because when the cosmic rays come to the heliosphere, and the magnetic field plays a role as a shield and can change this cosmic ray direction and protect the Earth, not so much from the bombardment of the cosmic rays. But for some planets, if their host star does not have very active magnetic activity and magnetic field is weak, it's more likely that the cosmic rays can penetrate more in their atmosphere. And indeed, these are ionization radiation, so it can change the biosignature, the ionization in their atmosphere. There's some study on that and show indication it could affect the chemistry in the atmosphere, the clouds formation there, and some, yeah, maybe some consequence on the biosignature in other planets. Yeah, there's also some study showing maybe there are some moments that cosmic ray would affect the global climate of our Earth long time ago. And also importantly, I guess it's also from the space forecast, the space weather. So people also care a lot about how the energetic particles from both space and the sun affect the spacecraft. So space weather forecast is also the frontier of a heliophysics study, and is also very much affect our societal benefits. Yeah, thank you.
One quick follow-up.
Mhm.
Can we measure the speed by which these cosmic rays are traveling and are within our galaxy or even from far away galaxy?
The speed?
Yeah.
Oh, so yeah, so I mean, these particles, so we measure the energy. So when the particle arrive at Earth, and we can measure the flux, the number of particles at a particular energy. So through the energy, we know, and we also know the species of the particles. We know their speed. But these are energetic relativistic particle, for example, about GeV is already relativistic. So all of them, you can just treat them as light speed particles. Yeah, so their energy milling just come from their kinetic energy, not the rest mass energy. Yeah. Mm-hmm.
Yeah. Thank you, Nas. So I'd like to pass the mic to Dash. Dash, are you able to speak?
Yes, can you hear me clearly?
Yes, we can.
All right. So I have a it might be a dumb question, but it's very fundamental. Oh, Miss Siyao, um, what is how do we describe a particle? Um, like, what is it that constitutes a particle? So, is this something that we detected with instruments, or is this a mathematical model?
Oh, so the cosmic ray particle here, these are milling protons. And there's some small fraction of helium nuclei, uh, electron positrons, and heavier elements, but 99% of cosmic ray are just protons. So it's, yeah, the dominant matter in the universe, yeah, in the interstellar medium.
Okay. So, uh, how do we def- so basically what I've been confused about, because I've been reading a lot about like nuclear physics and stuff lately.
Mm-hmm.
I keep coming across the reinforcement that photons are considered to be massless particles, and but we also have other particles that are matter that are considered to be matter. So what I up to this point, what I've always thought of as a particle is something that was material. But the idea that photons are massless and they're still considered particles, like basically what I'm asking, like how do what actually defines a particle?
Okay, so you say how do we define? Um, so yeah, I mean, so here I think we deal with just the classical definition of protons. So this is basically just the protons. Um, yeah, I mean, so this is believed that the pieces of matter coming directly from the universe, because it's a dominant matter. We believe, also in the interstellar medium, the matter to compose stars, for example. So it's the most abundant matter there, ready to be accelerated. So these particles, initially they are in the thermal pool, and by some acceleration mechanism, these abundant hydrogen atoms, these protons, get accelerated, and they are some of them, fortunately enough to reach very high energy. And if they can travel to Earth and we observe them, yeah. So yeah, I would say, whatever these energetic particles, so they are charged, energetic, and coming from the deep universe, and we call all of them as cosmic rays. Yeah.
Maybe it's my signal. Dash, I don't hear your question, or maybe, and also I think Dr. Siyao has already answered. It's proton that is regarding the definition particle, I think that's probably it's outside this. I think that it's more how to say the I guess it's a forever, it's a wave and particle, and it's become, I don't know. My personal feeling is that it's bordering line on the philosophy side. Yeah. Go ahead,
Gotcha.
Dash.
Understood.
If you finish, we can pass my mic to Kevin. Thank you.
Okay. All right. Thank you both. Thank you.
Thank you.
Yeah, thank you. And let's go to Kevin. Kevin, you might be speaking, but your mic is muted as of now.
Oh yeah, hopefully, I'm getting red bars. Yeah, my connection as well. So tell me if you can't hear me.
Yes, we
But
can.
I got most of this. But oh yeah, looks like another red bar. Yeah. So okay, maybe I'll try to hurry up. I don't know if you can speak on any of this, but as you said, the primary cosmic rays are mainly composed of protons and alpha particles. Like 99%, and a small amount of or heavier nuclei. It's really proportion of positrons and antiprotons. I'm just wondering how those interact, if we have a lot of data from that. And also, based on observations of neutrinos and gamma rays, some active galactic nuclei also appear to produce some cosmic rays. Is is things I've seen, and upon impact of Earth's atmosphere, cosmic rays produce showers of secondary particles. Some which reach the surface, and these secondary particles observed at sea level, while the primaries must be studied using high altitude balloons or spacecraft, as you mentioned. So I don't know if you can speak on any of that, and then also, hopefully it's not. Hopefully you can speak on too much of it, and also if your research contributes to the understanding of the ISM, the interstellar medium, if hopefully some of that's relevant.
Yeah, I'm not sure I capture everything, but I think you raised a lot of interesting points related to cosmic rays. So I would try to just so you mentioned the AGN active galactic nuclei. Yes, so in fact, just recent some detection of the high energy neutrinos come from nearby Seyfert galaxies, and where in the galactic center there is a very active process of the so the black hole there is being fed, and there's an active accretion process there. And yes, so yeah, I believe that the AGN activity is one of the mechanism in the accretion disk. So the material around the black hole, there can also be acceleration site for high energy protons in cosmic rays. So to explain the cosmic neutrinos that we detect directly, because that one we know exactly where it comes from because it doesn't interact with turbulent magnetic field. So we know their source direction, although we cannot directly find the corresponding cosmic rays because of their diffusion, but it's definitely believed there must be cosmic rays produced near these galactic center regions. And for you mentioned the detection, yeah. So there are ground-based and space-based facilities, and you mentioned this air shower of high-energy cosmic rays, and they produce secondary particles. That is what we detect on Earth by ground-based telescopes, and also so there are some recent space-based telescopes, and that can directly detect the relatively low energy cosmic rays below 100 GeV, basically. And in fact, it's very interesting. It's also very puzzling. The energy distribution, the energy spectrum of these different energy range of cosmic rays are found to be different. So early observations show a kind of like universal power law distribution for the particle energy spectrum, but more detailed observation from space and from ground start to reveal more details related to how these particles diffusively move in a different way depending on their energies. So yeah, I would say this subject has a lot of things to be studied, both in terms of their origin and in terms of how we confront the theories and new generation observations to understand the new observational puzzles. Yeah, I hope I hope I answer. I didn't really catch your question, but I hope I mentioned these different aspects that you nicely bring out.
Yes, I think you did. Yeah, hopefully I'm getting through. But yeah, and then also like I've been telling you, you're trying to get more acceleration, at CERN and Fermi or wherever. So I'll just mention, ultramagnetism. That's the new thing. I don't know if you heard of ultramagnetism, and it's not ready for prime time, but that's the only thing that came to mind as well.
Oh,
Thanks
okay.
a lot. Thanks a lot for all your.
Thank you. Yeah. Mhm.
Yeah, thank you, Kevin. And we have Carl, who also came up the stage. Welcome, Carl.
Hi. So if all we're seeing are protons, is there counterbalancing negative stuff that goes somewhere else?
Sorry, you said
If all we're seeing are
mean
protons, are there counterbalancing negative stuff that goes somewhere else?
okay. So yeah, we primarily observe protons. So you mean anti particles like
Supposedly the events that are generating these protons are electrically neutral.
I see. Okay, I see. Yeah. Yeah, that is a nice question. I mean, some accelerator produce current neutral particles like pulsars, but supernova remnants seem to, in terms of, so there are also electrons. So both protons and electrons get accelerated. So would I say cosmic rays as they can be detected by Earth on Earth? The problem with electrons, although they get accelerated, but they also lose energy easily, where the synchrotron emission near the source already. So yeah, they are both positive and negative charged particles both get accelerated, but we may not be able to detect them altogether on Earth. But yeah, near the source, they have different observational features corresponding to different charged particles. Yeah.
So the neighborhood around these explosions is negative charge because the mean impact for negative charge is actually much shorter than the protons.
I think I lost the part of your sentence.
So protons tend to travel longer than the electrons. And so then the local neighborhood of these events would actually have remnants of randomly, electrons being random walk in the nearby neighborhood, whereas the protons tend to get dispersed even further.
Okay, yeah, so that is a very interesting point. So yeah, so electrons they indeed they lose energy more easily than protons, and we do see this radio synchrotron emission from electrons. In fact, not just near the sources and also everywhere on the sky. Protons depend on the surrounding medium of the source. For example, some supernova explosion happens near in the galactic disk, and if there's a cloud of proton, this molecular cloud happen to be nearby, and then these protons from this particular source can be trapped along and also lose their energy by the hadronic process. So I guess it really depends, right? We also have we also have detection of electrons, positrons, right? Because their fraction is small, in general. So and also they have more energy loss. So we mainly just see protons on Earth.
Yeah, thank you. Carl, do you have any follow-up question?
Thank you.
Yeah, thank you.
All right. So, yeah, we've been here for about 1 hour and 30 minutes. And at this point, I always ask our guests as to how much more time do they have for us. So I'd like to address this question to Dr. Su now. Siyao, how much more time do you have for us?
Yeah, I'm happy to stay longer if there are more questions.
Yeah, thank you. So yeah, if those who are in the audience or other people here on stage, if you have more questions, please be informed that we are trying to give some extra minutes to for you to avail of this opportunity to be able to talk to our guest speaker. So just tap your mic. Yeah, if you have other questions. So I could see Kevin here. Kevin, I'd like to give the mic to you.
Oh, okay. Yeah, I don't know if I got through last time, but just a general question. Could you? Yeah, did have a question. Do you know if the research contributes the understanding of the ISM solar medium? Hopefully you heard that.
Yeah, okay, I heard. So you say how this, okay. Yeah, so for cosmic rays below PeV, we believe it comes from our galaxy. So to understand the diffusion of cosmic rays, and we do need to understand the magnetic field structure in our galaxy in the SM. So there are different aspects about the interaction between cosmic rays and interstellar matter. For example, if you talk about the electrons, by the way, I forgot to mention that because of this synchrotron cooling of electrons, so it's very difficult for electrons to reach so high energy as protons can reach. But we do use the synchrotron map, the distribution detected by Planck, for example, as method to study the interstellar magnetic field. So we need to, but to understand magnetic field, we also need to understand the diffusion of cosmic ray electrons. Then compare with the polarization measurement, the synchrotron intensity measurement to get the magnetic field, the clean magnetic field information in our galaxy. And low energy cosmic rays, it's more difficult for them to reach the Earth, also because they lose their energy easily, and they can ionize molecular clouds. So in these sites where stars form, in fact, these are very cold region, and cosmic rays plays a very important role to ionize the matter, the molecules there. So it happens in both the dense region in molecular clouds and also in the protoplanetary disk. So the matter needs to be ionized to couple with the magnetic field, and cosmic rays also play a very important role in their ionization and also chemistry in the star forming sites in our galaxy. So this is the star formation and cosmic rays are really closely related. So both the cosmic rays affect the star formation by changing the chemistry, the ionization, and also cosmic ray when you consider them as part of the energy carrier. So you can also think them as a kind of fluid. So you have the gas and you have magnetic field, and then you have cosmic rays. So it's part of the whole life cycle of the galaxy to maintain the energy balance, the pressure balance in the interstellar medium. And when the star come to the end of its life, it explodes. And also it becomes the huge energy released by the stellar explosion becomes acceleration site to produce new generation of cosmic rays and release them through the diffusion process back into the galaxy. So in our galaxy, because in general the star formation activity is low, but in some very active galaxies, with active star formation, and people see the correlation between the luminosity of these stars, the infrared radiation is closely correlated with the emission coming from cosmic rays, both from the radio emission from cosmic ray electrons and the gamma ray emission from the cosmic ray protons, and they closely related to the far infrared emission from the star formation. So it already shows the close correlation between the two processes. And in these galaxies, the cosmic ray as a driving force can also their pressure can push the gas out of the galaxy. So this is how the cosmic ray driven galactic scale wind can affect the evolution of the whole galaxy on the galactic scale. So we care about a lot of them on both small scales where the stars and planets form, and also on large scales and how the whole galaxy, the gas can escape from the gravitational potential of the entire galaxy on galactic scale, and how the cosmic ray as a momentum and energy form can affect the evolution. And also in galaxy clusters, now the radio observations now really can go to low frequency by LOFA, for example. So we start to see, in fact, these galaxy clusters appear to be much larger than what we earlier seen from the high frequency radio observations. So it's in fact it means these cosmic ray electrons in galaxy clusters somehow diffuse much further to much larger scale. They call it mega halos, and they are only recently revealed by low frequency radio observations on these huge size structures in the hierarchical structure of the entire universe. So there are many interesting things related to cosmic rays. Yeah. Mm-hmm.
Oh, that makes me think of the magneto-hydro dynamic MHD turbulence for playing a crucial role in physics for star forming molecular clouds and interstellar medium. Yeah.
Right. Yeah, I'm so happy you mentioned that. Indeed. So physically, we are so excited now. It looks like the cosmic ray diffusion now really enters a new paradigm because of our better understanding of MHD turbulence. So there are a lot of theoretical difficulties. So it's not real difficulties in nature, but there's a lot of theoretical difficulties in the last century coming from our not complete or correct understanding of MHD turbulence. But now with improved understanding, and we start to re-examine the detailed physics of the mechanism, for example, the mirror diffusion, I mentioned that. And the very interesting thing is all these early theories based on some assumption of linear small magnetic fluctuations, like wave-like oscillations of magnetic field, turns out to be not correct. The nonlinear MHD turbulence really brings a lot of new results and findings for the cosmic ray diffusion. And in fact, even today, we still use the diffusion, this word, as it's traditionally accepted in the literature. But in fact, if our recent study found it's not really have a normal random walk diffusive behavior. The cosmic ray, in fact, have a more like Levy flight propagation behavior. So it means the mean free path is not constant. It has the changing mean free path. It really depends on the interaction of particle with the turbulent magnetic field. So we know So when we say rapid flight, it's a bit like if we observe the propagation behavior of a fruit fly, and they do this rapid flight like, which means in some regions they are more spatially confined. In terms of cosmic rays, they are more spatially confined, have very small Mifree paths, and can be trapped for a long time in this particular region with, for example, magnetic mirrors. But in some other regions, they can smoothly move rapidly along the magnetic field and travel uh, uh, rapidly over a long distance with a very large Mifree path. So even we need to think about what is the new theoretical frame to describe this non-normal diffusive behavior. So there are a lot of, I would say, very, very recent new findings in this field, and it's really urge us to put more effort in this direction. And we know that because of so broad and far-reaching impact of this cosmic ray study, and it can bring probably many new insights into other branches of both in space physics and in astrophysics. Yeah.
Thanks a lot for your excellence. I can't wait to listen.
Thank you.
Yeah,
Thank you,
that's a very
Frank and Siyao. So, yeah, I'd like Siyao. Of course, you had mentioned earlier about the cosmic rays' impact on planetary environments, like in atmospheric chemistry. Like cosmic rays can influence the chemical composition of planetary atmospheres, including our Earth's, and they can initiate reactions that produce or deplete certain atmospheric constituents, such as the ozone. So, in terms of climate and weather patterns, there is an ongoing research into how cosmic rays might affect cloud formation and
Mm-hmm.
consequently climate and weather patterns on Earth. So, last time when Alex was here, we touched on, perhaps maybe on my case, it has tried to change my perception of how popular science is trying to talk to us about the climate change and
Mm-hmm.
yeah, so I would like to ask your opinion about this. Can you comment on what I said a while ago?
Yeah, I would say um, our human beings are really quite fortunate to live on Earth, and which is relatively, if you look at our local environment that detected by Voyager, we are in a very, so not only our galaxy is not a super active galaxy, our very local interstellar medium around us is also very quiet, quiescent environment. It is a good thing. Well, it may not be so interesting in terms of astrophysical or physical studies, but it's a very good thing for our human beings to be in a stable environment. So it doesn't have very active star formation going on nearby, and so the temperature and the turbulence level, everything seem to be in this is in the diffuse warm medium in the interstellar condition around us. And in terms of our sun, which is still not so old. So our sun is still actively have these strong magnetic fields produced by the sun, and that well protect the Earth in this environment, not so much damaged by the cosmic ray attraction. Uh, I would say um, I wouldn't so much about the cosmic ray effect on climate because I'm sure there are many, many other effects that can change the climate more significantly, um, including human activity. But in terms of the search for other possible planets that so exoplanet study, and people do well. This is still not well studied region that how the cosmic ray radiation would affect the just we discussed the cloud formation, the temperature, the global climate of other planets. Of course, it's because we don't really know very well the host star activity and what is their uh, uh, local environment is, uh, and how what is the so but there are more observations coming up to tell us the detailed signatures from the atmosphere of these planets, but there's not good there in terms of theoretical modeling of how cosmic rays can really affect the chemistry and the detailed biosignature there. I think this is a lot need to be explored and more. I would say we really need to put more attention to this aspect because it's really somehow overlooked effect when studying exoplanets. Yeah.
Yeah, thank you, Siyao. So, just one more question.
Mhm.
For what do you think are the new technologies or emerging technologies that's helping us to learn more about the cosmic rays? So earlier you had also mentioned about the space-based observatories like the Fermi and Gamma Ray Telescope and the Alpha Magnetic Spectrometer and the Pamela payload for
Mhm.
antimatter-matter
Mhm.
acceleration. And
Yeah.
yeah, and of course the ground-based detectors as well. So may you comment on this? And in relation to this, I would like to also ask how about data analysis and machine learning and artificial intelligence and digital twins? So, yeah, that's my question.
Yeah. So toward the future, um, so let me start from the uh, from let's say the theoretical modeling perspective. So now our simulation techniques significantly improved during the last decade. So early so there are different approaches for studying the cosmic rays on different length scales on different physical regions, and in particular now because of this they call it the particle in cell simulations. Um, it can from the first principle study the detailed macroscopic interaction between the charged particles and the magnetic field uh, in a very physically transparent way. And all of these simulations, as these are experiments, and these are very good tools for physicists to test their physical ideas or new theories. Um, so I would say this is a very good direction in terms of modeling. And for machine learning, so we know that cosmic ray physics is so complex because of their interaction with the turbulent magnetic fields, and which is a very chaotic behavior. And it's still not possible to analytically derive its behavior uh, over a long time scale. And we heavily rely on numerical simulations, so the computers to solve these basic physical equations, but we cannot really give a precise prediction on the turbulent and magnetic field behavior at a particular position at a particular time. So the machine learning has been also introduced into the field, uh, especially for prediction on the turbulent magnetic field behavior. And if that can, and also in terms of observational techniques, um, so Alex group also uh, involve machine learning to extract more information from the two-dimensional images. So unlike space solar wind observations, for astrophysical observations, everything we got is 2D. Everything we get is 2D. So it's always projected along the line sight. So machine learning is believed can play a very important role to extract the more physical information, for example, magnetic field and turbulence from the 2D emission images by comparing the 3D numerical simulations. So this, I would think, this is a very promising and powerful tool that AI can play in astrophysics in general, to get more information maximize the scientific return from all astrophysical observations. In terms of observations of cosmic rays, yeah, so I guess so. In from the direct measurements that you mentioned of this spacecraft to collect more data and for us to see the different species cosmic rays and their differences in spectrum. And now there are also a lot of like new information coming from gamma ray observations, for example, from LASSO, with very high energy coverage, and people start to feel start to see this they call it pevotrons. So we are pushing the limit that what our galaxy can do by detecting PeV photons by these very sensitive gamma ray telescopes, and we start to question what is the highest energy that the cosmic rays can be produced by our galaxy, and also how to understand the gamma ray distribution at different radii in our galaxy. So yeah, so to say that a lot of, in fact, the one of the biggest motivation for re-examining the cosmic ray diffusion study comes from the discrepancy between the existing cosmic ray theories and the new generation cosmic ray observations, including both the direct detection and also the gamma ray observations from these high energy protons. I would say in future, they would with the more detection of the high energy gamma ray photons, and it also motivate us to re-examine this shock acceleration model. And by the way, the shock acceleration, since the study by Bell, the Bell mechanism to explain the particle acceleration shocks, we still like working towards more progresses to understand how the particle can all the way accelerate it from the thermal pool all the way. Let's see, this is already like 10 orders of magnitude in terms of energy, all the way to PeV cosmic rays to explain the recent gamma ray observations. Yeah, and there's also next generation ground-based Cherenkov telescopes. So we will have like a more observational constraints or motivation from more observations to motivate us theorists to improve our understanding cosmic rays. Yeah, thank you.
Thank you so much. Yeah, it's very inspiring to hear you talk about this. And I was just reminded of some research that they did in artificial intelligence very recently. I think from the elite team of Leisa Guerra of Google. And I think there's also another study about emergence using AI. And I thought, of course, the cosmic rays are quite different, but then, with the weapon or the medium of exponential technologies that we had gained in the past years, especially I think in the past 2 years, we try to understand new physics and new science actually. So they were able to try to do a study about emergence using artificial intelligence and
Mm-hmm.
uh, very effectively through multitudes of data, billions of data. Just
Mm-hmm.
like the past years, we had AlphaFold, and it has now gone to AlphaFold 3. And the prediction that is being done is really very massive as compared to when it started. So, of course, I know that the cosmic rays are a different story, but I just wanted to comment on this because I'm just hoping, that this kinds of technology, which we do not expect now to be able to help us yet, will suddenly be able to help us understand and help in the study, very interesting study that you're doing in the future.
Yeah, I totally agree. And I forgot to mention how expensive all these numerical studies are. And despite the high computational cost and a lot of resources we are using, but still we are very, very far to reach the realistic inertial range. So everything I talk about is always like 10 orders magnitude in length scales, in energy range. But so far, even the largest simulation in the world MHD turbulence is just 2 orders of magnitude. So in terms of energy of cosmic rays, it's also limited to orders of magnitude, even by the largest simulation. So I would say if AI can help us to achieve a larger inertial range or energy range, because all these physical problems, they are multi-scale, um, complex problems. If the AI can solve this issue, I think it will be really, really fundamental breakthrough for us to understand this multi-scale um, uh, energization problem of cosmic rays. Yeah.
Yeah, thank you so much, Siyao. In case I would encounter somebody who's researching on AI who might be interested to address this question, I will try to connect them with you.
Yeah, that'd be great. Thank you. Yeah.
Yeah. Yeah, thank you so much. It has been a
Mhm.
very interesting discussion, and I could, if given the freedom, I would just like to listen to Sian until many more hours. But yeah, we are getting late, and
Uh,
Yeah.
we've been here for almost 2 hours. So anyway, Frank is trying to say something. So Frank, shortly.
oh yeah, I guess time flies. Yeah, very interesting discussions, by the way. Uh,
Yeah, thank you.
yeah, very mind-boggling. The earlier discussion, you and Kevin had. So I did a Google and Wikipedia. It's a rabbit hole. So much rich information. I from your slides that you shared, I had the question that I didn't ask earlier. Is due to no respect for others. You mentioned the shock waves that the wavefront being a possible candidate of accelerators. The so at this point these shock waves, you mentioned one mechanism is from the explosion of old stars. There's others, right? So by clicking, just hyperlinking the web, that I saw so many interesting physics that's so actively being explored, like often waves and shock waves from molecular clouds. And so what are the what is the status that can you share that at this point, that how certain is it, like as it's well confirmed, or the pattern, can we have a cost, it's like CMB, like we have a pattern mapping of where are the current active shock waves, or are these yeah, well, could you tell us, I mean, given that is it still a hypothesis of the acceleration of the accelerator, or is it already confirmed? Yeah.
Yeah, so thank you. So for the supernova shock in our galaxy, yes, it is indeed. So there are issues that when we observe a supernova remnant, it's usually already not so young, and we believe so that the most efficient acceleration should happen at the young stage of the supernova remnant. But the most observations, because they do not happen so frequently in our galaxy, which is now so active in general, so the most of the supernova remnants we observe are relatively mid age, yeah, a bit old, but we still see like non-thermal radiation coming from these supernova remnants, like both radio, X-ray, and also the gamma ray. So these non-thermal radiation definitely comes from energetic particles from the supernova shocks. And they also mentioned about the shocks in molecular clouds. So those shocks are weaker shocks, so their speed is not so large, so they do not have so large. They also can accelerate some particles, but they are not so efficient. They are not a dominant accelerators like the supernova shocks. And for shock picture, people also apply it to, for example, in gamma ray burst, where they call it internal shocks. So these shocks means these faster moving matter inside the jet, and that can also create a lot of shocks in the jet. But so I would say in our galaxy, because of these direct observations near the sources, these radiation near the accelerators, it's more convincing. But for more distant objects like these accretion disks near the black holes or tidal disruption events, like when the star is disrupted when it gets very close to the black hole, and also the gamma ray burst. So all of these, so we know they are very energetic. But the problem is that for cosmic ray observations, the degeneracy is too big in terms that different mechanisms because of a lot of physical parameters involved. So it is in a sense that they can somehow explain, all of them can explain the observations. So the observations, we have some energy spectrum from gamma ray or radio. So it's not so strong constraint from the observational side, at least from current observations, to really conclusively say which particular mechanism, for example, in this jet. So internal shock was believed in the last century to produce high energy particles. But the thing that IceCube didn't really detect high energy neutrinos from gamma ray burst. So now it is also a question whether gamma ray burst is also a very efficient accelerator of protons or not. Maybe there's not enough matter to be accelerated. And also there's also different model. For example, early time there were like thousands of models of gamma ray burst, and more recent observations put better constraint on gamma ray burst. It's also believed maybe the internal shock picture is now right. Maybe the most energy come from the magnetic field in the Poynting flux, or in that case, it's completely different mechanism. It could be the magnetic reconnection that accelerate particles. Yeah, so to say, indeed, we need more detailed observations to help us better constrain which model would be the winner in accelerating high energy cosmic rays in extragalactic environments. Yeah.
That's very, very interesting. Just quickly last, just to the linear curiosity from Alex sharing that. What's your thoughts on the primordial, the gigantic like magnetic field lines that are the very interesting pattern that have been observed?
So yeah, that is another unsolved problem, and so I personally don't have a strong preference on the particular model because there are so many models on the primordial magnetic field in the universe. I think the probably one popular is this battery mechanism, and also I would also say it's also very, very difficult. So these different theoretical models, they all seem possible to produce some very weak primordial magnetic field. But from the observational point of view, again, because today, after the dynamo process, we already lose the memory, so people can do the experiment no matter what kind of initial primordial magnetic field is, in terms of strength or in terms of correlation length. So the later dynamo process just wash out all the memories from the primordial condition in galaxies and galaxy clusters. The only hope we have is to through the detection of the intergalactic medium to put some constraint on the primordial magnetic field, and the rotation measure, for example, from faster radial burst also shows yes, it should be very, very weak. It doesn't seem to be important compared to other contributions of the rotation measures. And also there are some other blazar observations provide constrained, but also limited by, for example, Fermi's sensitivity. So it's not very clear. Um, so on one side, we are hoping observations can put more constraints on the characteristic of this on this primordial magnetic field. It is a very interesting question by itself. But on the other side, if people are interested in the magnetic field in galaxy and galaxy clusters, they seem to be already very well developed and amplified. Even we push the observations to high redshift. So even the rotation measured there in high redshift galaxies show the magnetic field is already coherent and strong, amplified by the mean field dynamo and turbulent dynamo already at early time of the universe. So yeah, I don't know much to say about the primordial thing. Um, yeah, I think it's very interesting theoretically, but I am not so well, I shouldn't say that, but I don't know like how accurate we can like constrain uh, what is the what is the correlation length, for example, what is the spectra of the magnetic fluctuations in a very clean primordial environment that we can push the limits to observationally. Yeah, I hope there will be new constraints coming up soon. Yeah.
Yeah, thank you. That's quite a treat. Yeah, thank you,
Mm-hmm.
Cecile.
Yeah.
Thank you so much, Frank, and yeah, thank you, Siyao. We have to really wrap up, and yeah, I'd like to thank you for coming. Even if we have a short practice time, it was indeed a very interesting conversation, and also with your eloquence on the subject, which I would like to appreciate. And I would like to give you back the mic, Siao, if you have some parting shots for us before we try to do our countdown. And of course, before that, I'd like Bob to speak if you wanted to. So for now, mic to you, Siao.
Oh, I just want to say thank you so much, and I really, really enjoy all your questions and appreciate them very, very much. And I think it's a really nice discussion. It inspired me a lot, and I appreciate this opportunity. As what I do is cross-disciplinary research, and I appreciate this opportunity to interact with you, working in different fields. And yeah. So so today, like I really feel that we need this collaboration from different disciplines to bring, and also you mentioned these AI techniques, and it will bring more scientific output from our research. So yeah, thank you very, very much.
Thank you. So, Bob, if you would like to speak, I'd like to pass the mic to you now.
I felt that this was a fascinating discussion, and you even brought up fruit flies, which is one of my favorite subjects. So I thank you on behalf of everybody in the room.
Yeah, as CEO, I hope
Thank you. Yeah.
we can invite you again in the near future. And just before I give the mic to Darcel to help us count down to close the room, how did you like your first Clubhouse experience?
Uh, sorry, is this for me? The question?
How did you like
Ah,
first Clubhouse experience with us?
Okay. Yeah, I really like it very much. I get very excited, and in fact, this is my first time to know there's such a wonderful form for people to connect and interact with each other. I feel very, very, yeah, although I'm not physically there, but I really get this atmosphere, the vibe that we are sitting around the fireplace and have the chat. Yeah, I really enjoy, and I do hope that I have another chance to come back to join you and yeah, join your discussion again. Thank you so much.
Yeah, well, there's so much that you can relate to us, so I hope we can do another schedule with you again. Considering the background that I
Mm-hmm.
told people about you in your bio, I'm sure that you have so much to teach us. So, anyway, I'd like to pass the mic now to Darcel to help us do the countdown to close the room.
Thank you, Cecile, and thank you, Doctor. Wow, energetic particles. That is very exciting.
Thank you.
You're welcome. To close the room, we're going to start our countdown from lucky number 6. Is everybody ready?
Ready.
6.
Ready? 6.
Kevin, 5.
5.
No, Kevin. Frank
Red bar
Quattro.
5, if you can hear me. Thanks a lot. You're the best.
Got you. Go ahead, begin, Frank.
Quattro. It is.
Ah, it is. Bob Thrace.
3 it is.
Lucille Dos Equis.
Dos Equis.
Good doctor, your numero uno. Call out our last number, please.
1. Thank you so
Number 1.
much.
Thank you,
Yum.
Leo.
See you
Thank you,
soon
Dr.
Thank
Shu.
in
Thanks, you're the
you.
best. I don't know if
Latinx.
you heard me.
Thank you. Bye.
Bye.